Hello, I am Dr. Sudha from Government Science College, Autonomous, Bengaluru. In this session, let us see some more types of differential equations which are reducible to exact differential equations. In the previous session, we have seen that an exact equation can be formed by multiplying by a suitable factor called an integrating factor. Also, we have found some rules for finding the integrating factors of the equation of the form mdx plus ndy equal to 0. In the previous three sessions, we have found by inspection, we have found for an homogeneous equation, we have also found for an equation of the type f1 of x comma y into y dx plus f2 of x comma y into x dy equal to 0. In this session, let us look into the equation mdx plus ndy equal to 0 other than the above three types. So let us look into the rules for finding the integrating factors of the equation of the form mdx plus ndy equal to 0. So in this equation mdx plus ndy equal to 0, if dou m by dou y minus dou n by dou x divided by n is a function of x, which is denoted by f of x, or if it is a constant, say k, then the integrating factor is given by e to the power of integral f dx, or it is equal to integral k dx if we get the function to be a constant when we calculate dou m by dou y minus dou n by dou x divided by n. Suppose if dou n by dou x minus dou m by dou y is a function of y, that is, it is f of y, or if it is equal to k, a constant, then the integrating factor is given by e to the power of f of y into dy, or it is equal to e to the power of integral k into dy. So these are the two types which we haven't seen in the previous sessions. So let us solve some examples on these two types. So solve x square plus y square plus 1 into dx minus 2xy dy equal to 0. So the solution is, so let us consider the given equation x square plus y square plus 1 into dx minus 2xy dy equal to 0. If you compare this with mdx plus ndy equal to 0, we get m is equal to x square plus y square plus 1 and n is equal to minus 2xy. Let us calculate the partial derivatives now. Dou m by dou y, that is when you differentiate partially m with respect to y, first term is x square, so with respect to y it is 0. Second term y square we get 2y, and the third term is 1, so on differentiation it becomes 0. So dou m by dou y is equal to 2y. And the partial derivative dou n by dou x, that is when we partially differentiate n with respect to x, we get minus 2 into y because x gives us 1. Now when we look into the partial derivatives, dou m by dou y is 2y and dou n by dou x is minus 2y, and these two partial derivatives are not equal. Therefore, the given differential equation is not exact. So let us calculate the integrating factor so that we can multiply by the integrating factor and make the given differential equation an exact differential equation. For this, let us consider 1 over n into dou m by dou y minus dou n by dou x. Dou m by dou y is 2y minus, so minus dou n by dou x is minus 2y. So we get 2y minus of minus 2y divided by n. So here we have taken 1 by n. So when we divide by n, that is minus 2xy. So this on simplification gives us 4y in the numerator, 2xy in the denominator. So now we can cancel out y and cancel 2 and 4 here to get minus 2 by x. Now this resultant function on simplification is a function of x alone. So the integrating factor is given by e to the power of integral minus 2 by x dx. And that will be equal to e to the power of minus 2 is kept as it is. 1 by x dx gives us log x on integration. So minus 2 log x in the power can be written as log of x to the power of minus 2. And we know that exponential and logarithmic function get cancelled and we get x to the power of minus 2, and that is written as 1 by x square. Therefore, the integrating factor is 1 by x square. So let us multiply the given equation by the integrating factor 1 by x square to get 1 by x square into x square plus y square plus 1 into dx minus 1 by x square into 2xy dy equal to 0, and this becomes exact now. So we all know that on simplification, that is by multiplying by 1 by x square or dividing this entire term by x square, we get 1 plus y square by x square plus 1 by x square into dx minus 2y by x into dy equal to 0, which is exact, and this is in the form of mdx plus ndy equal to 0. So this is the new m and this is the new n now. So we know that when the given differential equation is exact, the solution is given by integral m, that is 1 plus y square by x square plus 1 by x square, keeping y constant, plus an integral of the terms of n which are independent of x. Here no term is independent of x. Therefore, the next integral is 0, and that is equal to c. Now let us integrate this, keeping in mind that y is constant. So when we integrate, 1 becomes x, y square is kept as it is, 1 by x square gives us minus 1 by x plus 1 by x square once again gives us minus 1 by x equal to c. Now multiplying throughout by x, we get x square minus y square minus 1 equal to c into x. And this is the solution to the given differential equation. Now let us look into one more example of a different type. So solve y to the power of 4 plus 2y into dx plus xy cube plus 2y to the power of 4 minus 4x into dy equal to 0. So let us consider the given differential equation and let us compare this with mdx plus ndy equal to 0. So we get m is equal to y power 4 plus 2y and n is xy cube plus 2y to the power of 4 minus 4x. Now let us find the partial derivatives of m with respect to y and n with respect to x. So dou m by dou y is 4y cube plus 2 and dou n by dou x gives us y cube minus 4. Now these two are not equal. Therefore, the given differential equation is not exact. So to make it exact, we need to find the integrating factor. For that, let us consider 1 by m into dou n by dou x minus dou m by dou y. And that is equal to y cube minus 4, that is dou n by dou x, minus of dou m by dou y, that is 4y cube plus 2. This whole thing divided by m, that is y power 4 plus 2 pi. The numerator on simplification gives us minus 3 into y cube plus 2. In the denominator, we can remove y common. We get y into y cube plus 2. So y cube plus 2 gets cancelled and we get minus 3 by y. And this is a function of y alone. Therefore, the integrating factor is given by e to the power of integral minus 3 by y dy. So when we integrate the integral in the power, we get minus 3 into log y, because 1 by y dy gives us log y. Minus 3 log y can be written as log of y to the power of minus 3. Once again, the exponential and the logarithmic function get cancelled and we get that to be equal to y to the power of minus 3. And that can be written as 1 by y cube. Therefore, the integrating factor is 1 by y cube. Let us multiply the given equation by the integrating factor 1 by y cube to get 1 by y cube into y to the power of 4 plus 2y into dx plus 1 by y cube into xy cube plus 2y to the power of 4 minus 4x into dy equal to 0. And this is exact. Let us simplify this to obtain y plus 2 by y square into dx plus x plus 2y minus 4x into 1 by y cube dy equal to 0. And this is an exact differential equation now. So the solution is given by integral m, that is the new m formed here is y plus 2 by y square, keeping y constant into dx plus the terms of n which are independent of x. So the first term is x. So we need to reject this term. Second term is 2y. So this is independent of x. So consider that 2y. Next we have minus 4x into 1 by y cube. Even this term contains x. So reject even this term. So we get just integral 2y dy equal to c, where c is a constant of integration. Now let us integrate this term by term. So here y is kept constant. So 1 dx gives us x. So we get x into y plus 2 by y square is a constant. Retain that as it is. So 1 dx gives us x. Next come to the second integral. 2 is kept as it is. Y on integration gives us y square by 2, and that is equal to c. So now let us simplify this. 2 and 2 gets cancelled here, and let us multiply throughout by y square to get xy cube plus 2x plus y to the power of 4 equal to cy square, and this is the solution to the given differential equation. Thank you.